Welcome back. Last lecture, I went through nucleophilic attack and also reviewed the living groups. Now I'm going to go through protein transfer, and also we're going to review the rearrangement. And we're going to start with the protein transfer. We have a carbonyl group, and we have carbon with sp2 hybridization, and that's attached to oxygen and through a double bond. And we have a solvent or a molecule that it has hydrogen attached to it, and it has three of them. So that's going to be hydronium ion. It will behave like as an acid. And so in this case, I'm going to say oxygen that has two lone pairs. It will go after oxygen is going to go after hydrogen, and it will share lone pair. It will share two electrons or a lone pair with it, and this is going to happen. We get oxygen that attached to an hydrogen, okay, and hydrogen, it will give up those two electrons to oxygen. So we're going to get one molecule with two hydrogens. And of course, oxygen is going to have two lone pairs on it. And what's the charge for it? It will be 0. But our oxygen, the starting oxygen, is going to have a +1 charge because we shared one lone pair with oxygen, and oxygen technically came without any electron or just an empty orbital. This process, we call it a proton transfer. Okay, and so is oxygen happy with this case? Not really, okay, because oxygen, it has a positive charge. Oxygen, it can do this. Oxygen, it can take these two electrons and steal them from carbon. And if that one happened, then we get this structure. Let me show it here. I get carbon attached to two carbons, and here we will have oxygen attached to hydrogen, and oxygen is going to have two lone pairs. Now oxygen, it will have 0 as a formal charge, but carbon, it will have a positive charge, and that carbon, it can go and get involved in nucleophilic reaction. So if we get a nucleophile somewhere around, nucleophile, it will find this carbon, and it will share electron with that carbon. So the proton transfer says require two technically errors. One is to show where, like, which hydrogen we are attacking, and the second error is it's telling you that hydrogen that we are taking, that hydrogen, it will give up its electron and it will share it with technically oxygen. So this oxygen, it will take both electrons. Okay. Sometime, like, or most of, to be honest, like, and if you're talking about chemists, most of the time they want to avoid writing, big hydrogen molecule. They just simply write H plus, and that means H is an empty. It has an empty orbital. It can take in a lone pair from oxygen, and instead of hydronium, they write it as H plus, and the story will be exactly the same. You will get carbon attached to oxygen. Oxygen, it will share one of the lone pair, and we get H there. So I'm going to say this oxygen attacked hydrogen. Now we got oxygen with a positive charge. We can draw a Lewis structure for it, and this Lewis structure, it will be like this. They are the same. Honestly, there is no difference between writing H plus or hydronium. Only difference between them is going to be this. Like when you write hydronium, okay, when you write hydronium, the second particle, it will be one molecule. Here, we did not write it. Why? Because we know H plus, it cannot be inside the solution alone. H, it must be attached to something. And what's that? That's going to be the solvent or water. And we don't write water because it will make it easier to write the chemical reaction. Okay. Next part is going to be the rearrangement. And we have a term that we call it hyperconjugation. And what is it? Okay. And how this one is going to make the system more stable. The bottom line of this, like term is that carbon is not happy with a positive charge. Anything that can take the positive charge and drop it down, it will make carbon happier. Okay. Alkyl groups like CH3 or say ethyl, propyl, isopropyl, or say butyls group. Okay, any version of them, any alkyl group, there are electron donating groups. So electron donating group. Okay. And simply I'm gonna say alkyl group or electron donating group. And by sharing electron with carbon, the carbon with a positive charge, they will make it more stable. How this one is going to happen? Okay, it says if there is an alkyl group somewhere, forgive me, if there is an alkyl group somewhere neighbor with a carbon that it has a positive charge, it can use the sigma bond and share electron with the empty orbital on carbon and reduce the positive charge. Okay, let's talk about that. Okay, so the carbon that I'm going to highlight, this carbon is, it has a positive charge. So that means that carbon is not active and it's not, the electron geometry for it is going to be equal to the molecular geometry, and both they will be trigonal or trigonal planar. Okay, so it's completely flat. Okay, what's the bond angle? The bond angle here is going to be 120 degree. Okay, completely flat. Now, let's show the empty orbital on it. The empty orbital is going to be here. We will have a p empty orbital there. Okay, this orbital is empty. Next, we have a hydrogen. Okay, hydrogen attached to carbon, or it can be even a methyl group. Okay, it can be a hydrogen or methyl group. Okay, that hydrogen, okay, is attached to carbon through sharing electrons. So we have 2 electrons there. Okay, those 2 electrons are inside an orbital. Okay, this is the orbital that we're talking about. Okay, those 2 electrons all the time are moving. They are moving here. Okay, also they can move a bit down there. Okay, and why? Because the sigma orbital, it has 2 lobes. One is major, that is the bonding, and the bottom one is the anti-bonding. Okay, so electron can be, those 2 electrons, they can be here. Most of the time they are hanging here, or sometimes they get there. Okay, or they can, go there for a short time. Now, for a short time, those electrons, they go there. And if they get here, now we will have a negative charge. And what will happen? That's going to drop the positive charge. So any interaction between empty orbital and the sigma bond of, say, carbon-hydrogen or carbon-carbon is going to drop the positive charge. The positive charge is going to go down, and it will make the system happy, more stable. Okay? And term that we use for it, we say hyperconjugation. And hyperconjugation, whenever you have like a sigma bond, that sigma bond, it can share electron with an empty orbital on carbon. Okay, the sigma bond, it can be carbon-carbon or carbon-hydrogen bond, and it can share share electrons. Technically, any sigma, okay, any sigma. But if you have electronegative element, they will pull electron rather than share electrons. So you have to be careful about. We're talking about electron donating group. Okay, so alkyl group, we call them electron donating group because they can help the positive charge to go down, they can help carbon to drop the positive charge through sharing electron, through hyperconjugation. Okay, and now anyway, in any way, if you can make the system, make the positive charge less, that's gonna make the system happier. Okay, that's gonna make the system happier. And here that says we have methyl, primary, secondary, and tertiary. The tertiary carbocation is the most stable one. Okay, the tertiary. Why? Okay, let's talk about them. So we have a carbon that's attached to 3 hydrogen. And that carbon, it has a positive charge. That's the first case. Second case, we have a carbon that's attached to 2 hydrogens and a carbon. Of course, that carbon is going to be acted, so it will have 3 hydrogens, and we have a positive charge here. Next, we're going to say we have a carbon attached to 2 CH3 and 1 hydrogen. Okay. Next, we have a carbon attached to 3 CH3 and there is a positive charge, of course, on it. Okay, so I'm going to highlight number of hydrogen. We had 3 here. We call this one methyl. Okay, this is CH3. Now we got a carbon. Okay, we got a carbon that has okay, this is the carbon we're talking about. Okay, carbon used to be attached to 3 hydrogen. It's a methyl technically. Now there is a carbon attached to it. And which carbon? I'm talking about this. Okay, if you have only 1 carbon, that's gonna be, you know, primary carbocation. Okay, primary, we show it by 1, we put sign degree on the top of it. If you have two carbon attached to it, it will be secondary, and if you have 3 of them, it will be tertiary. Okay, look to number of methyls that they are attached to. Okay, a carbon with a positive charge. Okay, as we increase the alkyl group, the system will be more stable. So I'm gonna say the tertiary carbocation is the most stable one, then the secondary, next primary, and then you have the methyl. The methyl. Okay, in fact, these 2 are gonna be rare, or like you're not gonna see them. Okay, and so it's like the methyl CH3. That's not gonna happen. You're not gonna be able to catch in, you know, carbon that's attached to 3 hydrogen and still has a positive charge. That one in reality is not gonna happen because it's so unstable. If it's unstable, okay, if it's unstable, that means the activation energy for it is gonna be so high, and that reaction, it will not happen. Okay. Well, the tertiary, it has the lowest activation energy, so that's gonna favor the chemical reaction. Okay, the more alkyl group that you have, the higher stabilization you will get. The more alkyl group you have attached to carbon with a positive charge, the higher stabilization you will get. So the tertiary, it will be the most stable carbocation. Okay, now if you can rearrange the element in a way to get tertiary carbocation, or to get secondary instead of a primary, and then do it. Okay, and you can move hydrogen, or you can move a methyl, for example, a group. Okay, and first one, we're gonna do hydride shift. And what's the hydride? Hydride is a hydrogen, okay, hydrogen atom with a negative charge. That's going to be hydride. Okay, so that means we are going to move 2 electrons. Okay, so check this. We have hydrogen that's attached to carbon. We're going to take those 2 electrons and we move them to which carbon? We go 1, 2, 3, 4. We're going to move them to the 3rd carbon, and we're going to get this. So now we have hydrogen here. Okay, we got hydrogen there. Okay, We call this 1 and 2 hydride shift. 1 and 2 hydride shift. Now, what happened here? We got a positive charge. Why this one is a good thing to be happen? Okay, check the carbocation. Your carbocation now is a tertiary. It used to be secondary. So from secondary carbocation, we turn it to tertiary. So we had the secondary carbocation. We turn it to a tertiary carbocation. That's gonna drop the activation energy, and it will make the intermediate, okay. It will make the intermediate more stable. Okay. Anything that makes the intermediate more stable, it will favor the chemical reaction. So if you can move hydrogen with 2 electrons, that we call it hydride, and if you can move them to get a carbocation close to secondary or tertiary, then do it. System will be happy, and that's going to happen. Okay. Now, what if it's methyl instead of hydrogen? Okay, can I move that methyl group? Okay, let's see. Here we have a secondary carbocation. If I move this, I get such a thing. Put the CH3 here. So moved it there. Now we have a positive charge there. And this is going to be a tertiary. Well, it used to be secondary. So from secondary carbocation, we turn it to tertiary carbocation. And because we moved a methyl group, we call it 1 and 2 methyl, and then technically methide shift. Why methide? Okay, why is methide? Okay, methyl METH represent one carbon, but when you add IDE to it, you want to say that I shift this carbon with 3 hydrogen that it has -1 charge. So IDE stand for a negative charge. That means you moved those 2 electrons with carbon. Okay, and that's the reason we call it methide, like hydride. Hyd stand for hydrogen, IDE stand for negative charge. Okay, now, do I need to do this all the time? Okay, so as you see, we said if you can shift methyl or like a hydride group to get a carbocation that is more stable, then do it. But what if the starting point is already tertiary? Should I do? Okay, should I move this? Okay, and let's see. If we move, for example, if we move hydride, we get this. Okay, we will have a positive charge here, and hydrogen, we attached it there. We moved the hydride there. Now, what did I get? I had the tertiary, and I got the tertiary again. Okay, is it good things? Okay, if you look to it, now the positive charge is neighbor to a double bond, and because it's neighbor, it can get involved in resonance structures. So it can give you this resonance structure. Let me try to draw it as a zigzag. So I'm gonna get, okay, double bond here, methyl, and then we have hydrogen there. So what I did, I moved those double bonds. I moved that double bond here. I moved those 2 electrons, and I shared them with carbon that it has a positive charge. Okay, now what did we get? We got a positive charge here. Still, this one is tertiary. Okay, but I have to say this. The positive charge now distributed over 3 carbons instead of just 1 carbon. Okay, through resonance, we managed to distribute the charge over a bigger area. And anything that drive the ratio of charge to volume, if this one goes down, it will make the system happier and the system will be stable. I didn't change the charge. The charge still is +1, but the volume from one atom used to be localized, now is delocalized, okay? Because it's delocalized through resonance, okay? It's better to do 1 and 2, okay? 1 and 2 hydride shift, okay? And that's the reason it's gonna happen, because we get allylic carbocation, okay? And why don't you move? Why don't you move this hydrogen, this methyl? If you move this methyl group, you will get this structure. Okay, of course, we have hydrogen here. I get the positive charge there. Now our carbocation, it will be secondary. So from tertiary, we turn it to a secondary, and this is not a good move. Okay, I'm gonna stop the lecture here, and thank you very much.